Okay, this is Mr. Asher, and this is for Chem 121. And what I'm going to do today is I'm going to go through a short presentation on electronic structure of atoms, because we're not going to cover it in detail in this quarter, in this version of the course. And there's some interesting features of electronic structure of atoms that lead to periodic properties, which are the subject of the lab this week, Intro to Periodic Trends. So I thought I'd go through and give you the scientific, at least a brief introduction to scientific theories behind all that. And if you want to read more about it, this is from chapter 6 of the textbook of electronic structure of atoms. Anyway, so let me share my screen here. And so when we think about an atom, typically the canonical model we have is we have the nucleus here with protons and neutrons, and then we've got electrons that whirl around on the outside in these circular orbits around the side. And the actual situation is a lot more complex in what's going on, and it has to do with quantum mechanics and everything, and wave particle duality and things. But anyway, the short story is this idea that electrons are in these fixed circular paths and orbit around can't possibly be true. But there are elements of it that are similar. And what you find is if you look at what the structure of atoms really looks like, there we go, is that the electrons are arranged in shells. So we have this nucleus, and then we have, and the shells are numbered from 1 to infinity, although we really know 6 or 7 in most atoms. And so the innermost shell is n equals 1, and that'll have some electrons in it. And then there's a shell that n equals 2, and that'll have more electrons, and n equals 3. And the structure of electrons in these shells is integrally related to why the periodic table looks like it does. And we'll go through what that means in this talk. But you can think of it now as, instead of having electrons in circular orbits around the atom, what they are is they populate in shells. And inside these shells are what are called orbitals. And these orbitals all have these very strange shapes. And there's different types of them. There are what are called s orbitals, p orbitals, d orbitals, and f orbitals. And if we had larger atoms, we would have g orbitals too, but those aren't known because nuclei that large aren't stable. But think about all these electrons that are whirling around in these shells, or populating these shells, and then these are what these shells look like. So the one type of shell is called an S shell, and it's spherically symmetric. And then there are these p orbitals. It looks like dumbbells. So they have one here oriented along the x-axis, one here oriented to the z-axis, and one oriented to the y-axis. And the thing about these orbitals is why they look like they do is, if you add them all up, if you superimposed all these on top of each other, what you'd get is something with spherical symmetry. And so all of these orbitals sort of add up to get something that's spherically symmetric. And that has ramifications to the periodic table too, which we'll go over in a little bit. And these are d orbitals, and you can see they're even more complicated. And again, you kind of sort of maybe see a little bit that if you add them up, you're going to get something with spherical symmetry. And here are f orbitals. And again, if you add these up, which we're not going to do, but if you add up all of these lobes and squish them together, you'll get something that's roughly that is spherically symmetric. Okay. So let's look at more detail at these spherically symmetric s orbitals, because what we're going to do next, we'll follow over to all of them. So if you look at this shell number, the principal quantum number 1, 2, 3, what you see is that this is that these orbitals give you a probability of finding the electron at any distance or location, radial distance out from the center of the atom, and then at some XYZ angle going around the atom, right? And these are spherically symmetric, and this means that the probability density of finding the electron at a certain distance from the nucleus has got this one bump here, and this is the 1s orbital. And for a 2s orbital, it's got these two lobes, and you can see that the maximum probability is farther away from the nucleus. And the 3s orbital, it's even farther away. And this is typical as the quantum number goes up, the size of the orbital increases in terms of moving the maximum probability of finding the electron farther and farther away from the nucleus. And since the nucleus is positive charged and the electrons are negatively charged, you want the electron close to the nucleus because that's the lowest energy. So we talk about these levels having the 1s being lower energy than the 2s, and that's just because the electron is closer to the nucleus in the 1s than the 2s on average, right? And so that's what's going on with these orbitals, is that the electrons move farther and farther away from the nucleus, and these orbitals all have different shapes. And it also turns out that these s orbitals, which are spherically symmetric, have the lowest energy of all the other orbitals. And so here we're plotting the energy of these orbitals, meaning how close they are to the nucleus and the energy of the orbitals. And what we find is the 1s is lowest, followed by the 2s. And then there are these two p orbitals. Remember, the p orbitals are the dumbbell-shaped ones. And then 3s, and then 3p. And then we've got 3d orbitals here, but we find that the 4s orbitals have a bit lower energy than the 3d orbitals. And that will come into play when we look at the periodic structure of the structure of the periodic table in just a minute. So it goes 4s, 3d, then 4p, and then 5s and 5d. And what you can see is these orbitals sort of are going up in energy, right? And if there were g orbitals, they would be out here somewhere, right? There would be the 4d, 4f, 5g orbitals would be way out here off the screen to the right. Okay, so that's what's going on, is these orbitals tell you where the electrons are in these shells. So these are all electrons in the second shell, the 2s and 2p, and there's only 2 electrons and each one of these orbitals contains 2 electrons. So there's 2 electrons in the 1 shell. There are 2, 4, 6, 8 electrons in the 8 shell. There's in the 2 shell, there's 2, 4, 6, 8, 10, 12, 14, 16, 18 in the 3rd shell, and then correspondingly more in the 4th shell, and then the 5th shell, and then the 6th shell, right? Okay, so how does that correlate to the periodic table? And so this is how the periodic table is laid out. And here up at the top is hydrogen and helium, and you could see these are the 2 atoms that have electrons in the 1s shell, right? And then lithium has got 1 electron in the 2s shell, and beryllium has got 2 electrons in the 2s shell. And then boron, carbon, nitrogen, oxygen, fluorine, and neon, those electrons for those atoms are all in the 2p shell. Now keep in mind that as you go up, you not only have electrons in these topmost layers, but there's also electrons in these innermost shells. So for example, copper, right, which is down here in this shell, it's got a bunch of electrons in the 3d shell. It's 4s shell. The 3p is the 3p orbitals are filled, the 3s orbital filled, the 2p orbitals are filled, the 2s orbital filled, and the 1s orbital are filled. So copper down here, what did I say? Copper, chromium, no, copper. So copper has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So copper will have 29 electrons, okay? Oops, I got that right, yeah, 29. So copper has 29 electrons, and of those 29 electrons, the outermost electrons are the 2 electrons in the 4s shell, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in this 3d shell, right? So that's what's going on, and that's why the periodic table has this sort of columnar look to it, is that these columns correspond to electrons in a particular orbital in a particular shell, right? And they fill in order of energy. So the 1s fills first, and then the 2s, and then the 2p's, then the 3s, then the 3p's, and then the 4s's fill. And then remember back on our energy diagram here, right? 4s was lower energy than 3d. So once the 4s's fill, then you start to fill the 3ds, and then you fill the 4p's, and then the process starts over again here, okay? And so we can write these electronic configurations here. We'll write it as these are just the configurations of electrons in the outermost levels. So we'd say aluminum has 3s2, 3p1, meaning it has outermost electrons are 2 in the 3s orbitals, 2 3s2 orbitals, and 1 in the 3p1 orbital, a 3p orbital, right? Oxygen has 2 in the 2s orbital, and then 4 in the p orbitals, 1, 2, 3, 4. And what you see is that the electronic configuration in the outermost electrons is the same going down in a column. Fluorine has 2s, 2s2, 2p5. Chlorine has 3s2, 3p5. Bromine has 4s2, 3d10, 4p5. But the important thing is there's a 4s2 and a 4d5. Iodine, 5s2, 5p5, right? So again, you find that there's the same thing here going down. In each column, the atom will have its electrons in the same configuration in terms of types of orbital. And electrons in the same type of orbital is what determines the chemical processes. And that's why things in a column on the periodic table behave the same chemically. Oxygen behaves pretty much the same as sulfur. Nitrogen and phosphorus are similar. Carbon and silicon are similar. Lithium, sodium, potassium, rubidium, cesium all have similar chemical properties. Hydrogen is a little bit different, somewhat the same, but hydrogen and helium are sort of their own special categories because these are just the s orbitals, right? But another example is over here, what are called the noble gases: helium, neon, argon, krypton, xenon, radon. These all have fully filled outer shells, and so they're all spherically symmetric, and that's a very stable electronic configuration. So these things aren't very reactive, which is why they're called noble gases. Okay. So anyway, what you find is because of this similarity in electronic structure, there are periodic properties to these atoms here. And that's why it's called the periodic table, because things happen periodically. Scandium is the same as yttrium, right? Titanium and zirconium behave sort of the same. Chromium and molybdenum are the same. It's the same as tungsten going down this column, right? Okay. And so for example, copper, silver, gold, these are all the precious metals. Well, silver and gold were, and silver and gold behave similarly as they do to copper because they have a similar electronic configuration. Okay. So let's look at how some of these periodic properties are the same. And let's look at radius, right? Remember I said that helium, neon, argon, krypton, and xenon all had filled shells and were spherically symmetric. It's not coincidental that they also have the smallest radii of any element in their group, right? So that as you go down here, you get to the spherically symmetric electronic configuration, and it sort of pulls in because it's energetically favored, so it tightens up and the electrons lie closer to the nucleus. Sodium with just one electron in an outer atom has got a huge electronic radius, a huge radius comparative to argon, right? Even though it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer sphere, its outermost electron is not bound that tightly to the nucleus, so it's way out here. Whereas this with 8 more is pulling in. Okay, and you see these trends over and over. Potassium going all the way down to krypton. And these are the transition elements. So all of a sudden now these are the d orbitals here, right? And these are the d orbitals here. And so you could see that there are these sort of trends that if you look just at the p orbitals, which are these black dots here, They come down all the way to krypton. So here's the p orbitals here. So bing, bing, ding, 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 right? And the d orbitals sort of get in the way here. But again, you see the same sort of trend here, over here for the for period, let's see, 1, 2, 3, 4, 5, for period 5, right? Okay. So hopefully you see that's happening. And because of that, you get some interesting facts about interesting features of what's going on. So for example, here you have aluminum atom, non-charged atom, neutral atom, and its atomic radius is 118 radius units, which I think are angstroms. I can't remember. I'd have to look that up. But then you'd move these 3 electrons, and all of a sudden now you've changed its electronic configuration to something that's more more energetically convenient for the atom, and its radius shrinks. Okay. Now sulfur, on the other hand, it wants to gain 2 atoms to get to a spherically symmetric full shell. And so when it does, its atomic radius increases. So this is a sulfur atom that's gained 2, right? And just to go back, just to give you a little bit more, something I should have mentioned before, is where an atom is sitting here along the periodic table will determine whether or not it generally wants to gain or lose electrons. For example, every atom wants to come out with a spherically symmetric distribution of electrons. And so, for example, fluorine sits 1 to the left of neon, which means that if it gains an electron, it will have the same electronic configuration as neon, which is energetically favorable. So fluorine really wants to gain an electron. Same thing for chlorine, bromine, iodine, acetane, right? All of these things here in column 17, which are called halogens, really want to gain 1 electron to form a singly charged anion. So fluorine minus, F minus, Cl minus, bromine minus. And that happens because it wants to gain an electron. Oxygen wants to gain 2 electrons. When we go and do bonding, you'll see that oxygen always has an ionization state of -2 because it gained 2 electrons to try to get to neon. Nitrogen will want to gain 3. Carbon can go either way. It can gain 4 or it can lose 4. And depending on the compound it's in, you will find it doing both, right? And then all of these metals generally will have oxidation states that are losing electrons. Cobalt can have, chromium can have +7, which is 1, 2, 1, 2, 3, 4, 5, 6. Chromium, 1, 2, 3, 4, 5, 6. Now chromium loses 7, or maybe it just goes to 6, +6. So when chromium loses 6, it's all the way down here. It's lost all of its outer shell electrons. Chromium can also lose 4, 1, 2, 3, 4. Gets it over here, so it just has the 1s and 2s in its outer shell. So all these things can be sort of understood, at least in a kind of a hand-wavy sense, by losing electrons. A lot of these elements over here will lose the 2s electron. There are 2 electrons in the s shell to form a +2 cation. Iron is a good example of that, which iron +2, and then iron also forms a +3 atom, a +3, where it loses 1 electron from its d shell to give it 1, 2, 3, 4, 5, a half-filled d shell, and then it loses both of its s electrons. So anyway, if you go into the details, a lot of the ionic structures of these atoms can be explained in terms of the orbitals and where it sits on the periodic table. So be aware of that. We're not going to go into a lot of detail on that. Be aware of it. There is a theoretical reason for that. We just, I just decided it wasn't particularly relevant to, it's a lot of fussy details to memorize, and I didn't think it was particularly useful for people to memorize all that stuff. So there's atomic radius, and that's sort of what's going on in terms of atomic radius and why that's like it is in terms of electronic structure. And there's ionic things, but you can also see it in terms of other properties of atoms. Here's ionization energy, and this is the energy it takes to rip an electron off an atom. And what you can find is these things down here, the alkali metals, lithium, sodium, potassium, rubidium, cesium. It doesn't take very much energy to remove that electron. And you see that when you look at the atomic radius. Sodium has got a huge atomic radius, given that, its electron is far away from the nucleus, which means it's easier to pull it off than for helium, which has a much smaller atomic radius, spherical shell, doesn't want to give up that spherical symmetry. Neon doesn't want to give up the spherical symmetry. So it's really hard to rip an electron off. Fluorine, again, fluorine would rather gain an electron, so it's hard to take that electron away from fluorine, and it's got a much smaller radius, right? So if you plotted ionic radius with as a function of ionization energy, you would see a fairly good correlation between ionic radius, between atomic radius and ionization energy. And you might want to try that in the lab that you're going to do with this, okay? And the final one I'm going to show you is electronegativity. And this is how much an atom wants to acquire an electron. And so a high value of electronegativity means the atom really wants to get an electron. Low value means it doesn't want an electron very much, right? So these down here in purple are, this is hydrogen. So here's sodium, lithium, and then beryllium, and then sodium and manganese and potassium, and I forget what the other one, calcium, right? So, and again, you can see that this electronegativity goes up generally along a period until it peaks at the halogen. So these are the halogens here, and then you drop, and they don't have electronegativities for the noble gases on here for some reason, which I don't understand, but they should. But this is the peak of the halogens, right? So 1, 2, 3, 4, 5. So this would be fluorine. This is chlorine, bromine, iodine, and astatine, and so forth. Okay. So remember, when you look at this periodic table, that the columns are there for a reason, and they have to do with electronic structure. Okay. That the things over in these two columns, helium is 2s, so it really should be over here, but it fits better over here in terms of noble gases, right? But these over here are s orbitals, and these atoms tend to want to lose electrons. Things in the middle here are d orbitals. Things down here, which really slot in here, these are f orbitals, all the f orbitals. And over here are p orbitals. And then again, this is the noble gas column, where things are spherically symmetric. And so depending where you sit, you either want to gain electrons to get a spherically symmetric shell or a noble gas structure, or you want to lose electrons to go the other way, right? So that's all I have to say. Hopefully you'll find this with a little bit of use and not too confusing. And I'm going to stop sharing my screen there, and then I will quit for the day and talk to you later.